But to kind of pick up where we left off, we're talking about how big is an atom, and it's all about what the electrons are going to do. So this, if you take the periodic table, just focus on group A elements, take the B out. We have this trend as you go down the group, we call these groups, or down the group, it gets larger, but as you go across the period, it gets smaller, and we need to kind of talk about that today. So this is finally a new slide. I didn't get to this slide on Monday. This is finally a new slide. So it goes something like this. If this is my nucleus, I'll put N for nucleus. Well, I better make it a little more explicit. Inside my nucleus, I have, of course, protons and neutrons, okay? And then I have my electrons out here. Let's just go ahead and throw a couple electrons out there. Okay, we'll make it helium. Okay, it's all about kind of what volume my electrons are going to give me. So this slide emphasizes the idea of the attractive forces would be make it smaller. Attractive forces means electrons are being attracted to the protons. That makes it smaller. Okay, and the repulsion between the electrons, the repulsion makes it larger. Okay, that makes sense. So attractive forces make it smaller, attractive forces being between the electrons and the protons. And if those electrons are fighting each other, they're repulsing from each other, it's going to fluff out, make your atom larger. So in this, where we're focusing on how big is an atom, it's kind of a battle between those two forces. Every atom has those things going on. Okay, repulsion between each other and attraction to the positively charged nucleus. So a lot of stuff to enter that one. All right. And just in general, I would remind you guys, I am recording these, so if you miss a slide here or there, you can always go back and listen to my recording. Okay, so this idea of getting smaller as we increase the number of protons, it gets smaller. What's up with that? Well, that must mean that the attractive force is increasing. Okay, so that's, I'm going to we'll do a couple problems and then I'll kind of show you why that is. It's something called effective nuclear charge. It's all about the getting smaller across the same period. Because as you're going across the same period, element to another element, increasing the number, remember that's the atomic number of protons. You're also, if it's neutral, increasing the number of electrons. So it seems to me, as you're going across, increasing protons, you should both be increasing your attractive forces and your repulsive forces. So why does it get smaller? So I feel like I have a lot of slides that say the same thing. That's why it gets hard for me to say. I don't want to just read the slide. Yeah. But again, the attractive forces get stronger, it gets smaller. The repulsive forces increase, it gets larger. Okay, so let's do a problem like you might have to wrestle with. So I've got a whopping 5 elements here, and I would ask which atom of this element is larger. Order them. We're going to arrange them in order of increasing atomic size, from smallest to largest. And you're going to see my first thing is to grab your periodic table. Okay? So find those on your periodic table and draw circles around them. And they will look like this. These are your 5 elements that we're curious about right now. Notice that I picked only group A elements because this trend of decreasing size from left to right and increasing size from top to bottom, that's only the group A elements.
Wait, repeat what you just said?
It's only for the main group elements.
That rule only applies to the...
Main group elements, yeah. And I have a slide here to kind of show you where the transition elements kind of have their mind of their own with regard to atomic size. But here they are without the periodic table. Okay, so does this make sense that, well, first off, okay, we said that size, how do we say this? Size increases going down, and we said that size decreases going from left to right. Okay? So does this make sense that your fluorine is going to be your smallest one, okay? And your cesium is going to be your largest one right off the bat? Yeah. Good. So now we just have to wrestle with phosphorus, sulfur, and calcium. Okay. Now, I've gone ahead and done the builds here. This whole phosphorus sulfur thing, the fact that they're in the same period means we can make a judgment call that the one on the left is larger. So phosphorus is larger. Mm-hmm. Yep. But do you see where calcium actually is in the period after phosphorus and sulfur? So it's going to be larger. It's going to be larger than both phosphorus and sulfur. Yeah. It's a whole period down. Yep. So then after phosphorus, we pick up calcium, and then after calcium, like you said, we pick up cesium. So cesium's our largest. And I'm trying to think, with any pair, should you be able to figure it out if they're A elements? And yeah, I think you should be able to. It's like a little logic game. Okay? So to me, the only catch is this whole phosphorus-sulfur thing. That's the only catch, I think. If it's in the same period, it actually gets larger as you go from right back to left again. And there, in cute little picometers, is how big they are. From those are atomic radii, I think, from the nucleus out to the edge of the electron cloud.
Do we need to know this?
No. Nope. So I said the B elements don't play along, so I won't give you on your test anything about these elements. So notice that it looks like as you're going from left to right, so the B elements are right here. As you're going from left to right, it looks like there is kind of a trend, but it kind of breaks down. So these guys right here. Okay, looks like it's smaller and then it gets larger. So just one more kind of tidbit about why that trend across the period is for it to get smaller. It's all about something called the effective nuclear charge, which the symbol for the effective nuclear charge is Z star. Okay. And I have a little, I put together at my desk like a little kind of show of how this works. So effective nuclear charge is Z star, okay? And you can, Z star actually describes the attraction for the valence electrons to the nucleus. Remember we talked about valence electrons are highest N. We'll be talking more about valence electrons in Unit 3.
That's like when we did like the 1s2 and then the valence electrons would be the highest number.
Right, the valence electrons are the highest N. Yep, those are valence electrons. Do you remember that we can use the group number to know how many valence electrons each element has, if it's in a group A element? Yeah. So it's those kind of last, they're not the last added, but the highest, they're valence electrons that kind of are what are responding to this, okay, to kind of do what it does. So the other electrons are called inner electrons, and actually the inner electrons give this sort of shielding effect. Okay, so in order to understand, kind of focus on those cute little valence electrons, what we do is we take the shielding electrons, okay, and we subtract that from the number of protons in the nucleus. Okay, so I'm going to do an example. And then that is the effective nuclear charge, and that actually is kind of what those valence electrons are seeing. Yes?
You said the valence electrons were the same as the group
Number.
number?
Mhm.
Okay.
Yep. Yep. So I'm going to pick on two elements. I'm going to pick on magnesium first. Magnesium is atomic number 12. It has 12 protons, and so it has 12 electrons. And these are how the 12 electrons are configured. 1s2, 2s2, 2p6. The valence electrons are in red up there. There are 2 valence electrons in the 3s subshell. So to calculate the effective nuclear charge, Z star, we take the number of protons, which is 12, and from that we subtract the shielding electrons, which is 10. Okay? So these valence electrons, they see a +2 nucleus, right? So let's go ahead, and magnesium is in period 3. Let's pick another element in period 3. Can't remember which one I did. I picked phosphorus. Phosphorus is also in period 3. Now, magnesium and phosphorus, which one is larger? Magnesium is larger. Very good. So let's see why that would be. So the phosphorus atom has 15 protons, and here's how those 15 electrons around a neutral phosphorus atom are configured. So looks like I missed my superscript 6. I can add that back in there. Okay, so we kind of have these inner electrons. They're in black. And then we have these valence electrons. How many valence electrons do we have? 5, exactly. It's a 5A element. Well, that all works. So now if we calculate Z star, it looks like this. 15 protons. We have the same number of shielding electrons as we did for magnesium. We have 10 shielding electrons. So we have 15 minus 10. So the effective nuclear charge is a +5. So it's almost kind of, I think of it as a little independent thing. These red 5 valence electrons are actually attracted or drawn to a +5, whereas those 2 valence electrons are drawn to a +2.
Where do we get the -10?
The -10 are the inner shielding electrons. So if you count 2 + 2 + 6, the black ones are your 10. Yep. So that's why there's more of an attractive force going on for those 5 valence electrons. So that's why phosphorus is smaller. Magnesium is larger. Bottom line. So now finish my slide. So what I just described to you, effective nuclear charge, what you saw were those in the case of period 3, they were 10 shielding electrons. Okay. And it gave different effective nuclear charge. Right. Yep. Magnesium is bigger than phosphorus.
And that always applies even when they're not in the same period.
No, it only applies when they're same period. Like the example we did a minute ago, I think had calcium, phosphorus, and sulfur or something maybe like that.
Right.
And when you step down from period 3 to period 4, by golly, calcium is bigger than both of those, phosphorus and sulfur. Yeah. Okay, so these will be due when you come. These will be due, I guess, on technically the Monday after your little break. I know, no school Friday. Yeah, so let's take a quick look. I think these are okay for you guys, though. But notice that on that, the outline for your test tomorrow, there will be problems. What I usually do is a pair. I can't remember what I've done for you guys this semester. Just to say which one's larger, which one's smaller. Now, if you ever face which one's larger, which one's smaller, like on a test, be sure that you read the question carefully, because what you don't want to do is mix it up. Just take your time. You guys got 2 hours for your test. You don't need 2 hours, but you have 2 hours. Yeah. And we're in room 314. Did I say that before?
So the same thing.
In the same room, yep. So these would be, I think you'd be fine. I'm not gonna, you gotta use a periodic table for this, right?
Yeah.
Totally. No guessing. You got a 50-50 chance, but don't guess. Okay?
Okay, so